Hello, my name is Chris Hayes, and I am a postdoc here at the Hertzberg Astronomy and Astrophysics Research Center in Victoria, Canada. And I'm excited to talk to you today about our new results coming from the Gemini high-resolution optical spectrograph GHOST. So GHOST is a new high-resolution optical spectrograph that's installed down at Gemini South. And it's got two different observing modes. It's got a single object high-resolution mode with a resolution of about 75,000, and a standard resolution mode which can do up to two objects simultaneously with a resolution of 50,000. In addition to that, it's got a very large wavelength coverage from about 3,600 angstroms all the way out to about 10,600 angstroms. So you get simultaneously all of the optical region as well as a little bit of ultraviolet and infrared. And this makes it a very powerful tool for studying a wide range of different science cases, from exoplanets to stars to extragalactic systems like nuclear star clusters and globular clusters. Now, of course, making a new instrument takes an entire team, and so I just wanted to highlight some of the integration and commissioning team members that were involved in putting GHOST together and making it such a success. And so you can see up here you have the members of the Australian teams at the commissioning of the Cassegrain unit for the instrument, which is the part that connects it to the back of the telescope, as well as you've got the Canadian team some of the Canadian team members shown down here, standing in front of the outer enclosure of GHOST, where the spectrograph sits during operation. So really what I want to talk to you today is some of the first science results from the commissioning of GHOST. In particular, we looked at a pair of stars in the ultra-faint dwarf galaxy Reticulum II. Now, commissioning is something that isn't done every day. It's something that only happens when you start to put new instruments on telescopes. And so really what the goal of commissioning is to test the performance and verify of an instrument and make sure that it meets its requirements. Now, in addition to this, we also wanted to include some science observations just to make sure that we understood how this new instrument GHOST works in more realistic observing conditions. So things like faint targets, looking at long exposure times, getting a range of different signal to noise so that you understand how the instrument performs in high and low signal to noise cases. And so we had a couple different science targets that we observed during the June and September commissioning runs of last year. And one of these was to look at a pair of stars in the Reticulum II ultra-faint dwarf galaxy. So this is a class of galaxies that are extremely faint and dark matter dominated. For instance, Reticulum II has an absolute magnitude of about -2.5, which means that it's about 1,000 times brighter than the Sun, but it's only one galaxy, as opposed to the Milky Way, which it can be hundreds of millions, billions. In addition, we know that ultra-faint dwarf galaxies are relatively metal poor, and in the case of Reticulum II, it has a metallicity of about -2.5, which is about 1/300th of the metals that's in the Sun. The most interesting thing about Reticulum II, though, is what I'm showing over here on the right. It's the fact that Reticulum II is significantly enhanced in what are called R process elements. So the R process, or rapid neutron capture process, is a type of nucleosynthesis that's only produced in extremely high energy environments like neutron star mergers or supernova jets. And this is a rare case of a galaxy that is significantly enhanced in these R process elements. So what I'm showing is europium to iron ratios as a function of metallicity. Both of these are relative to the Sun and on a log scale, so that 0 is the same as the Sun, a factor of 1 is 10 times more than in the Sun, and a factor of 2 is 100 times more than in the Sun. And so with increasing europium to iron ratios, that tells you you've got an increasing amount of R process enhancement. And we can see that the Reticulum II stars here in red are significantly enhanced relative to other ultra-faint dwarf galaxy stars in these colored points, as well as most Milky Way field stars in gray in the background. And so this makes Reticulum II a very interesting test bed to explore the R process enrichment and see what different kinds of origins it can have. So in particular, we wanted to observe a new star in Reticulum II. So this shows an on-sky distribution of likely members of Reticulum II as well as the 2 stars that we've observed during GHOST's commissioning. So these high probability members were selected using a methodology that was developed here at Hertzberg and the University of Victoria by Alan McConaughey and Kim Venn, and is being updated by a graduate student at the University of Victoria, Jacqueline Jensen. And so this picks out high probability members, and you can actually see over here that in the Gaia color magnitude diagram, these stars nicely trace an old metal poor isochrone. But the interesting thing about one of these targets, which had not previously been observed with high-resolution spectroscopy, the point in red actually falls to the red side of these old metal poor isochrones. Now, you could explain this with 2 different ways. It could either be relatively metal-rich, or it could be enhanced in carbon, which can make your star look a lot redder than it typically would. Now, recently, there was a paper by Alex Xi and collaborators earlier this year that showed that this star, where they've measured this small red point, has a metallicity that's actually consistent with other Reticulum II members, which are shown here in black and blue. And you can see here our measurement as well is in very good agreement with that. So what this suggests is that this star is probably enhanced in something like carbon. And that's exactly what we find. So this shows an example of ghost spectra for a metal poor benchmark star up here at top in gray, as well as the 2 Reticulum II stars that we observed. And this shows a region around the magnesium B triplet. So those are these strong lines that you can see here. And this is a region that shows off some of the different features that we can actually see in this star that make us think that it's a little bit of an odd star. So in particular, what we can see is that despite the fact that these 3 stars all have similar metallicities, this new Reticulum II member has extremely strong magnesium B triplet lines, as well as this molecular feature here, which comes from the C2 molecule. So in particular, because this is made up of 2 carbon atoms, it's rare to find this strong of features in metal poor stars because they have so little carbon. The only times where you see this is if they're very enhanced in carbon. And similarly, you shouldn't see these strong of magnesium lines unless it was also very strongly enhanced in magnesium. Now, with the ghost spectra, we can actually model these using synthetic stellar spectra, and we can calculate the chemical abundances that are in this star. And so that's what we've done for a number of different elements. This starts off by showing this calcium and magnesium, and you can see that, as expected, the magnesium and carbon abundances are significantly enhanced relative to other Reticulum II members, shown here in black and blue, and even most Milky Way field stars. Now, carbon and magnesium are produced through nuclear fusion in a star during its lifetime and distributed through supernovae. If you go to heavier elements like calcium and manganese, these are elements that are produced in supernovae explosions. And in these types of elements, we actually see that this star is fairly similar to other Reticulum II members. So it's very interesting that it's not enhanced in all elements. However, if you do go to heavier elements still, the neutron capture elements like barium and europium, what we find is that this star has fairly typical chemical abundance ratios for Reticulum II stars, which means that it's enhanced in the R process like other Reticulum II stars. And so just summing this up, showing the abundance ratios relative to iron as a function of atomic number for a whole bunch of different elements that we can measure, we see that this star is not only enhanced in carbon and magnesium, but it's enhanced in a whole bunch of other light elements. If you go to heavier elements around iron, the so-called iron peak elements, we see that it's fairly typical in terms of its chemical abundance ratios. And then if you go to heavier neutron capture elements, you see this classic R process enhancement pattern. Now, because we see the R process pattern in a whole bunch of different Reticulum II stars, but we don't see the light element enhancement, that suggests to us that this light element enhancement is coming from a different source than the R process enhancement, which is pretty typical and in line with what's been seen in Milky Way halo studies. Instead, this light element enhancement is actually something that's seen in some stars in other ultra-faint dwarf galaxies. So you can see the same chemical abundance pattern showing up here in some of the stars of other ultra-faint dwarf galaxies. And what these are called they're called CEMP-no stars. So these are carbon-enhanced metal poor stars that don't have neutron capture enhancement. And so what we think is that this star is one of these CEMP-no stars that has also had an R process event pollute its atmosphere. And so the interesting thing about these stars is that we actually think that these CEMP-no chemical abundance patterns might have been produced in the supernovae from the first stars, the zero metallicity POP3 stars as they're called, and that produces an overabundance of light elements relative to something like iron. And so it's interesting that we've found one of these stars in a galaxy where we have the R process abundance pattern, because we can actually time the R process in this galaxy. And doing so tells us that the R process event and mixing of that gas should have taken about a few 100 million years, which is a little bit at odds with what you would think for a POP3 star. You would think that the first stars in a galaxy should have had supernovae very fast after that galaxy was formed, and then that gas would have been either well mixed or lost to the interstellar medium. And so the fact that we see this light element abundance pattern only in one star out of several that have R process enhancements suggests that maybe this isn't the only way that you can produce these abundance patterns. And so this gives us an opportunity to start to understand what is the source of the CEMP-no abundance pattern, as well as compare it with the R process timing. So with that, I'd just like to say that hopefully you've taken away that we've identified this new chemically peculiar star in Reticulum II, which is an interesting dwarf galaxy in its own right, but the fact that we're seeing this star with CEMP-no-like abundance patterns lets us do more with it in the future. And hopefully you've forgotten already that this is an entirely new instrument, and this is the first time that we're doing any science with it, so that it encourages you to do your own science with it in the future. Thank you.